if you are as comfortable with fractions as you are with whole numbers, this method will do. And I want to give you an option for if you are not as comfortable with fractions as you are with whole numbers. An option that will allow us to get to the same answer, but sort of front load a lot of the fraction thinking that we had to do in the process of using just straight up reversing the order of operations as we did here. Here's how this method gets started. We start with an equation like this one that has fractions all over it. Every one of its coefficients happens to be a fraction, but this method would work even if only one fraction were present. So as soon as you see a fraction in an equation, you can choose to use this approach. And the way the approach works is by observing that any time we do the same thing to both sides of an equation, the same arithmetic to both sides of an equation, that's an okay thing to do. Our new equation is still going to have the same solutions as the old one did. And so whether we want to add something to both sides, subtract something to both sides, multiply something on both sides, divide something on both sides as non-zero, any of those equations afterwards is going to tell us the same thing that the equation did beforehand. And so what we'll think about this time is there something that we can do to this equation on both sides, because we have to do that equation, but is there something that we can do to wipe out the fractions? Can I turn all fractions in this equation into whole numbers? And that's, of course, a rhetorical question, because the answer is yes. The question is what? What can I do to a fraction that can make the result into a whole number? Like, let's suppose that I want to set my sights on this -3/2 on the left side of the equation. Is there something that I could do to that -3/2 that will make the result into a whole number? What do you think? One way to turn -3/2 into a whole number is to multiply it by 2. Where'd you get that 2? 2 is the denominator, right. So that is a possibility. If I multiply -3/2 by 2, let's do that fraction arithmetic just to convince ourselves about why this works. -3/2 times 2, well, how do I multiply a fraction by a whole number? Yeah, turn that whole number into a fraction by putting a 1 in the denominator. And then what's going to happen when I carry out this multiplication? Actually, I'm going to do it in a sneaky way. I'm going to do it by interchanging these two denominators. Multiplication is commutative, after all, so I can trade the order in which I multiply. And that is true in the denominator as well as it is true overall. So what I can do here is trade out the 1 and the 2, and so what I end up with is something that looks like this. But then what's 2 over 2? 1. And what's -3/1? Yeah. So by multiplying -3/2 by its own denominator, what I'd end up doing is I end up with an expression that has only just the numerator left over, which is a whole number, necessarily, by definition. So that's great. That step will get rid of the fraction on the left-hand side of this equation. What's the catch? I have to do to the other side too, right? So I can't just multiply the left side by 2 without also multiplying the right side by 2. And so then I'll have some more work to do, right? I'll have to multiply, let's put it in parentheses, I'll have to multiply both of the terms in this expression by 2. And -2/7 is going to turn into -4/7. I'm going to skip over that fraction multiplication there. -9/5 is going to become -18/5. So we've made some progress. We've gotten rid of one of the fractions, but we still have a couple more that we might want to deal with. So what's a way that we could deal with one of these two? What can I do next if I want to get rid of another fraction? If multiplying by 2 is enough to clear out this fraction, what can I multiply by next if I want to clear out another fraction? Let's say I put my target on this 9/5. If I wanted to get rid of that 9/5 and make it into a whole number, what could I multiply by?
5.
For the same reason that multiplying by 2 cleared the denominator of negative 3/2, multiplying by 5 will clear the denominator on my, well, not negative 9/5, I guess. I should have highlighted negative 18/5. Right? Multiplying by 5 will clear that denominator. In fact, it'll turn negative 18/5 into just negative 18. But of course, the catch is that I can't just do it to one of these quantities. I have to do it to all of them on both sides. So multiply by 5 on the left-hand side. Well, that's nice because that's going to remain a whole number for the rest of the process, right? Negative 15. And then negative 4 over 7 multiplied by 5 is going to turn into negative 20 over 7. And you might stop right now and say, oh, it sure seems like we're doing a lot of steps compared to the method we were using before. I agree. We're going to try and package this all together into one step in a minute, but just to look one little bit at a time right now. So that multiplying by 5 is now taking care of this denominator. So what do you think my last step is going to be if I want to get rid of this last denominator? Multiply by 7, sure. If I multiply on both sides by 7, negative 15 times 7 is, I believe, negative 105. Negative 20 over 7 multiplied by 7 will clear that denominator. And then I just have to multiply negative 18 times 7, which is going to give me negative 122. Wait, negative 120, negative 126? Yeah. Whew, right. And so at the end of that whole process, at the end of that mess, comes an equation which has no fractions left in it. Negative 105 equals negative 20u minus 126. And this equation will have the same solution that our original equation did, but it has only whole numbers left. And so once we get to that stage, we are prepared to reverse the order of operations, where all of our arithmetic is going to be only whole number arithmetic. I'm going to go through those steps reasonably quickly because we've seen them a number of times by now, and because I have a larger point to make. But if I add 126 to both sides, I'll end up with, let's see, 21 equals negative 20u. And then if I divide both sides by negative 20, I'll end up with u equals negative 21 over 20, which was the solution that we got last time when we solved this just directly using fraction arithmetic and reversing the order of operations. This looks like more work because when we did it last time, just reversing the order of operations, we had more or less just 3 steps, right? We had to add something to both sides, and then we had to divide by something on both sides, and that was it. And this step seems like it added in some more work up front. It added 3 more steps, if we look at it this way. But this is not the way, broken out in this way, is not usually the way that people do it. Very often people will do this whole thing here in a single step. In other words, rather than multiplying by 2 followed by 5 followed by 7, they'll go forward and just do this multiplication all at once. So my question to you is, what's the total amount that I've multiplied by in getting from this first equation at the top down to this last equation on the bottom? What's my total multiplication that I did there? Multiply by 2. What happens if I multiply by 2 and then by 5? How much have I multiplied by in total? By 10. And if I multiply by 10 and then I multiply by 7, then the total that I've multiplied by is 70. So rather than seeing this as 3 separate steps, what's usually done, just to save time, is we usually conceive of this as a single step. So we can do the whole thing all at once by multiplying by 70. But then you're going to ask yourself, or you should ask yourself, how would we have known 70 was the right thing to multiply by in the beginning of the problem if we didn't break it out step by step the way that we just did? Where could that number 70 come from this original statement of the problem? So this 70 came from all of the denominators in the original equation mushed together, right? Really, if we multiply all 3 of those denominators by each other, 2 times 7 times 5, that gives me 70. And that gives me a number which is a common multiple of 2, 5, and of 7. Right? And that's what we need, because anytime I multiply a fraction by any multiple of its denominator, we're going to get a whole number. So that's the principle that's at work here. Right? So to get this process is often called clearing denominators. So in case I use that phrasing later on, that's what this method is referred to as, or sometimes clearing fractions. I prefer to call it clearing denominators because it focuses you on the part of the fraction that's going to help with this process the most. So it'll always be okay, it'll always be enough for us to just multiply the denominators that we see together, and that gives us a number that has sufficient composition to cancel out all the denominators that we see. And so we could just look at this and say 2 times 7 times 5, that's going to give me 70, and then I'll just multiply both sides of the equation by 70. Just like when we're finding common denominators for adding fractions, that's the kind of method that's brute force and it will always work. Sometimes it'll give you numbers that are bigger than you need, but it will always give you numbers that will work in the process. So let's just swing through this real quickly just to check what the arithmetic would look like if we did this all at once. Because this is sometimes the step this is where you invest your mental energy when you use clearing denominators, is you invest it in this one step so that you don't have to keep investing energy into fraction arithmetic later in the problem. So let's take a look at just the left-hand side, 70 times negative 3/2. We know that if we've chosen a good common multiple, if we've chosen a common multiple, then this product needs to come out to be a whole number. And one way of doing it is, again, just to multiply straight across, 70 times negative 3, 1 times 2, and then reduce that fraction. But that's not, in this method, the one that I prefer. I prefer to do this trick that we talked about a minute ago, which is take the two denominators and just flip-flop them. Right? Because multiplication is commutative, we can use that property applied to the denominators to rewrite 70 over 1 times negative 3 over 2 as 70 over 2 times negative 3 over 1. And the great part about that is that each of the two factors in this product are now whole numbers. Negative 3 over 1 is negative 3, and 70 over 2 is 35. And then I just have to multiply 35 times negative 3, and that's where my negative 105 comes from. So my favorite aspect of this method is that when we use the method of clearing denominators to solve an equation like this, we never end up needing to add fractions, we never end up needing to subtract fractions, we never end up needing to divide fractions. The only fraction operation we'll ever have to do when we're using clearing denominators is multiplication of fractions. And that's the most straightforward operation we can do, because it doesn't require a common denominator, it doesn't require any keeping, changing, or flipping. The only innovation that I use when I do this is to just trade the two denominators, so I'm doing whole number arithmetic again. And if you can work your way through that minefield, it's a much safer minefield than one in which involves multiplication, or addition and subtraction of fractions. So if we did that same process for these two terms, we would get the negative 20u and the minus 126. And from there, it's just reversing the order of operations using whole numbers only.